This is lecture 5 for week 7 of CS 1030. In this lecture segment, I would like to basically just finish up talking about two's complement. I know that this is somewhat difficult material and there's kind of a lot going on, and I just want to kind of review and repeat some things to try to make sure we understand. So, as we've seen, the value of an n-digit unsigned binary number, that is to say a binary number that's only representing non-negatives, is represented by this formula. So it looks complicated, but it's not. All it's saying is you take the bits, we count up the bits from 0 to n minus 1, where 0 is the LSB, the least significant bit, and bit number n minus 1 is the most significant bit. And we take each of those bit values and we multiply it times a power of 2. And so this is exactly what we've already learned. So all this is saying is that the value of, for example, the bit at position 0 is that bit's value, so either 0 or 1 times 2 to the 0, which is just 1. So of course, we already knew exactly that the value of a binary number, of the least significant bit of a binary number either contributes 0 or 1 to the value of the binary number. Okay, so all this is saying is we sum up the values contributed by each of the bits, and each of the bits is worth twice as much as the preceding bit because the powers of 2 keep increasing by 1. Okay, so the other thing we can look at is how to determine the value of a 2's complement number that's the same size. And it's exactly the same formula, except that instead of the most significant bit contributing a large positive value, as we see here, we've stripped off the term for the most significant bit, and we've placed it in a separate term here where it contributes, instead of a large positive value, a large negative value. That is to say, of course, only if that bit holds a 1. If that bit holds a 0, then we have 0 multiplied by the large negative value, and it doesn't contribute anything. So all this is saying is the interpretation of the value stored in a fixed width binary number is almost the same between, depending on whether that's a regular binary number or a 2's complement binary number. They're almost the same. The only real difference is the contribution of the most significant bit, which is either a large positive value or a large negative value if we're doing 2's complement. Okay, so let's take another look at this stuff. So let's look at the number wheel again. And here I have a binary number wheel, and it's a 3-bit binary number wheel. So it goes from 0, 1, 2, 3, 4, 5, 6, 7. So as long as we keep adding 1 to the value, we go clockwise around the binary number wheel. On the other hand, if we have our binary number wheel and we keep subtracting 1, we start at 0, then we go to 7, 6, 5, 4, 3, 2, 1, and we go back to 0. Okay? So let's look at a different way to look at the binary number wheel. So again, we have a 3-bit binary number wheel, and we start with 0 at the top. If we count up using regular numbers, that is to say not 2's complement numbers, if we count up, we go clockwise, 0, 1, 2, 3. Nothing happens when we pass here. We go to 4, 5, 6, 7. But when we add 1 to 7, something very special happens. We would have carried out a 1. That 1 gets dropped off the end of the number. We have an overflow, and so we go from 7 to 0. Okay, so now let's count up in 2's complement. So we start at 0 again. We keep counting up. We go 1, 2, 3. Now here's the thing. When we pass from 3 to what would have been 4 in the 2's complement system, we have an overflow. We can't keep counting up because 3 is the largest representable number in a 3-bit binary number system that's representing 2's complements. So instead we wrap around to -4, then we keep counting up, -3, -2, -1, and then 0. So in one of the representations, we have a discontinuity between 7 and 0 when we cross this border. In the other representation, we don't have a discontinuity here. We have one over here where we have a wraparound from 3 to -4. Okay, and so again, no matter which representation we choose, the number wheel works almost the same, but the values represented by some of the numbers change. And this is this kind of somewhat confusing thing that we just sort of have to, as computer programmers, get used to. This is just how it works. Okay, so let's return to this question. How can we tell whether some number stored in a computer is stored as 2's complement or not stored as 2's complement? And another way to say that is if a byte contains all ones, or FF, how can we tell if that byte is meant to be interpreted as 255 or -1? And the answer is there's no way to tell. We have to have some external context. I've said this a couple times before, and I just want to repeat it because it's super, super, super important. We just need to know externally whether that particular byte, FF, represents 255 or -1. You can't tell by looking at the actual value. Thank you.